Hello, and welcome to Radioisotopes Nuclear Applications Beyond Energy. Presented by the American Nuclear Society, this evening's event is part of our educational training program specifically developed for elementary through high school teachers. I am Eric Lowen, Chief Engineer for GE Hitachi Nuclear Energy and former ANS President. I am pleased to have the opportunity to moderate this webinar featuring Julie Ezold on applications for nuclear science beyond energy. Before I introduce Julie, I'd like to cover a couple of quick notes regarding today's event. If you have any questions, please type them into the Q&A function in Zoom. We will attempt to address as many questions as possible. The event will be and is being recorded, and a link to the recording will be emailed to event registrants tomorrow. Additionally, certificates for attendees for today's event are available by request. Please see the chat for contact information. And finally, we ask that all participants adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found at our website at ans.org. So with those notes out of the way, I'd like to introduce our special guest. Julie Ezold has 30 years of experience in nuclear sciences at Oak Ridge National Laboratory. Currently, she's on a detail assignment with Department of Energy's Office of Science Isotope Program Office as a technical advisor. Previously, she was the Californium-252 Program Manager, a multi-million-dollar enterprise that includes the production of berkelium, einsteinium, and other transcurium products. These transcurium products have been used in the discovery of a new element 117, discovered in Tennessee, aptly named tennessine. So if you want to see that, there is a Wikipedia page if you'd like more details. In addition, she has held the position of radioisotope production and the operations section head, responsible for managing the production and optimization of all radioisotopes that are in a continuing and sustained state of demand and production beyond the research and development phases. Julie holds a Bachelor of Science in Nuclear Engineering from RPI, a Master's in Nuclear Engineering from North Carolina State University, conducting research at Oak Ridge's National Laboratory with the high-flux isotope reactor. With that master's completed, she joined the staff at Oak Ridge National Laboratory and has held positions in engineering, waste management, criticality safety, and isotope production. Julie has also been active as an American Nuclear Society member since 1988, where she now currently serves on our board of directors and is also the chairperson of our Scholarship Policy and Coordination Committee. She's also been active with the U.S. Women in Nuclear, better known as WIN, since 2003 and currently serves on the National Steering Committee. Julie, we turn the webinar over to you.
Thank you, Eric, and thank you for this opportunity. I really appreciate it since it's something I'm very excited about. So isotopes, what are they good for? So we'll go over what is an isotope. So I won't read to you, but isotope is the same element, but a different number of neutrons. So if we remember our chemistry, the nucleus is made up of protons and neutrons. So if we add more neutrons, we have the same element, but it's now called an isotope. Sometimes these isotopes can be too energetic, and then they're considered unstable. They need to decay, and they can give off some form of energy, either as a particle or as a wave. Radioisotopes and stable isotopes are found in nature, but they can also be made in nuclear reactors, particle accelerators, or we can generate them from other isotopes that are decayed, and we will talk about that. So what are the possibilities? Again, I'm not going to read the slide, but possibilities are endless for the use of radioisotopes. So we're going to just cover some areas. There's more to look at, more that you can take a look at. And at the end of the presentation, I have a lot of websites that I got this information from and that you can also take a look at and discover more for yourself. But nuclear batteries, being able to harness the energy from that radioactive decay and turn it into energy is what nuclear batteries are. So for example, We have the heat source, this lovely red one on the left. That is actually a pellet of plutonium-238. That is what NASA uses for energy for its deep space missions. That one, we're actually using the heat generated from the radioactive decay and converting that into electricity. We also have types called beta voltaics and also beta photovoltaics. That is using the energy of the beta source, the beta particle that was given off during radioactive decay, running it through either a scintillator or through a semiconductor transducer to make the energy. So you're converting that beta energy into energy that can be used for other applications. This is a very busy slide, and I apologize, but continuing that, we give you some abbreviations on the right. So when we use these terms, like electron volt is EV, a Curie is a measurement of radioactivity. It's actually based off of Marie Curie. It was the amount that was given from 1 gram of radium. But we can look at different radioisotopes to see what that energy is, that electron volt per decay. And each one of these has a different level that's given off. And from that, you can convert that into the watts or the joule per second. So in this example of strontium-90, basically we're saying if you want 1 watt, now remember, our light bulbs are typically 60 watts, so just 1 watt of energy, you would need 155 curies of strontium-90. But that's a thermal energy. That needs to be converted into what would be a watt of electricity. And that has a very low efficiency right now in our nuclear batteries. So you can see you would need significantly more strontium-90 activity to get 1 watt of electrical energy. So those are some of the areas that we're looking at as being more efficient in our nuclear batteries, is that conversion from thermal energy to electric energy. We also have some applications that we can use, but looking at the bottom chart here, you can see what the transducers are. So whether it's a thermal electric, which we talked about with the RTGs, the radioisotope thermal electric generator, or a voltaic or a photovoltaic, you can see the power levels. And again, only talking hundreds of watts. And even here, we're talking microwatts. So 1,000th of a watt or a milliwatt, or which is I'm sorry, microwatt is 1/1,000,000th and milliwatt is 1/1000. So you can see these are very small levels compared to, again, going back to 60 watts for your light bulbs. But what would we use these for? You want to use these nuclear batteries in environments that possibly there's no sunlight. So deep space, deep sea. You're not going to get the solar. So the solar panels aren't going to work out in outer space once you get far enough away from the sun. And they're not going to work in deep sea because the sunlight can't penetrate all the way through to the bottom of the oceans. So this is where these nuclear batteries have great potential for applications. So what are some industrial applications? So we're going to switch gears a little bit, looking at different isotopes for this. We can use different radioisotopes for different applications. Most folks have an older style smoke detector in their home. That's this picture over here on the left, where it actually uses an americium-241 radioisotope that gives off alpha particles. Alpha particles cannot penetrate a piece of paper. They can't penetrate the outer layer of your skin. So in a smoke detector, what it's doing is those alpha particles are very close to the sensor senses those. And as long as it senses, everything is good. But if something gets in the way, like smoke, like steam, then the sensor can't sense the alpha particles and therefore says we have a problem. And that's when you get that very loud siren that comes off of your smoke detector. So when you've had a smoke detector that is near your bathroom and you open up the door and all the steam comes off, that's why the smoke detector goes off. Or in the kitchen and something is in the oven and it's given off some smoke, your smoke detector is working appropriately. Another area is pest control. So fruit flies, they can actually use a radioactive source to sterilize the male fruit flies so that when the women go to meet up with them, you are not going to have any future fruit flies. Airport security, if you've ever had to go through and your items were swabbed and then they took them over to a detector, what that detector is using is a nickel 63, which is a beta source. It is using a ionization mass spectrometer. It's using that to see, will their signal be given off for any kind of chemical compounds that might be considered explosives. In addition, you have gamma radiography that can be used to look for any kind of cracks, either in the welds or in the pipes. So what this allows you to do is kind of like an X-ray, but you're using gamma sources. So if you think about the pipelines way out in remote areas, you can't bring the X-ray machine there, but you can bring these very small handheld devices that are used remotely using a radioisotope source that can penetrate and give you a vision back of if there is a crack in that weld. And the last example I've given on here is looking for thickness, whether it's for sheet metal or for paper or any other industrial material. You can use a beta source to look, and based on how much of those betas get through, will give you an idea of how thick the material is that you're measuring. Another really fascinating area in today's science is quantum information system. Basically being able to use quantum effects for computation. It will not replace our current computers, but it has an application where we can do more computations faster. But to do that, we need isotopically pure silicon and germanium in order to make these devices. Also, the silicon-28, if it's isotopically pure, is being used to improve the heat conductivity in these computer chips. So again, very novel new applications of these isotopes, but also very exciting. Even though we said this was going to be beyond power, I would be remiss if I didn't lay out some of the isotopes that we do use in the fusion reactors. So in there for the fuels, we use deuterium and tritium, which are just isotopes of hydrogen. The deuterium has 1 proton, 1 neutron, and the tritium has 1 proton and 2 neutrons. Also uses helium-3 and boron-11 for different types of fuels. And then the blanket material uses the lithium-6 isotope. For fission reactors, whether it's a pressurized water reactor or a boiling water reactor, we can use fuels like thorium-232 or uranium-235. And then we also use uranium-234 for monitoring the flux levels so that we can make sure that the reactor is operating at the optimum level. And then boron-10 is used because it loves to absorb neutrons. It has an affinity to just suck them up like a sponge. So they can use those to monitor and regulate the neutron flux inside the reaction. Medical isotopes have phenomenal uses. We recognize them for, it can be used for treatment and diagnostics. They're being used today for cancer trials, both in the United States and across the world. But we also can use a lot of these in biotech. This gives you a listing of all the different medical isotopes that are available and those that we are actually are under development. So you can see there's a whole suite of these that are both alpha emitters as well as beta emitters. So a term you might hear sometimes is theragnostics. So theragnostics is a combination of diagnostics and treatment. So this could be the same radioisotope, or it could be a pair of radioisotopes working together. And that's what we've laid out here is some of the ones that we are using in the aid in diagnostics and imaging. So imaging is one way to go in and see what is happening inside the body. A PET scan, a positron emission tomography, it usually uses a very short-lived radioisotope that's injected into the patient, and it will follow where the most active regions of the body are. Typically, your cancer cells will be the most reactive. And so you can see that in the scan. This one I put in here, SN117N, SN stands for tin. It's a very old Latin word for tin, but tin 117M is actually being used in treatment, in veterinary treatments of dogs with arthritis. So I thought that was really fascinating that we're using medical radioisotopes in veterinary science. Cobalt-60 has been used for decades. It can be used to sterilize single-use medical. The gamma rays are very effective in sterilizing any instrument. Also been used for food irradiation, where you actually could expose your food to gamma radiation, and it destroys any of the microbes and bacteria, viral, and allows your food to have a much longer shelf life. The biggest one is spices. They've been irradiated for years. Strawberries have shown, if you could do food irradiation on them, have a shelf life of 2 to 3 weeks. I mean, that would just be wonderful in the summer. But also cobalt-60 is used in a medical treatment for external beam therapy. They can actually focus the gamma rays to specific spots. This is typically used in brain tumors. Just because of the blood-brain barrier, a lot of other medications and treatments can't cross that barrier. So an external beam is what is necessary, and the focus of the beam is so that you can minimize any damage to the healthy tissue around where the tumor is. This final point right here on the slide is showing using copper-67 is a diagnostic demonstration, so that copper-67 is one that is coming online and the lights up when you do the imaging. So another area of medical applications is targeted radiotherapy. So the radiotherapy can use alpha particles, which is a helium nucleus of 2 protons and 2 neutrons, a relatively large particle with a lot of energy, but it doesn't travel very far. As I mentioned in the americium-241 smoke detector example, they can't penetrate even through a piece of paper or the dead skin layer, but they can penetrate a few cell widths, so they can actually get into the cancer cells and deposit their energy and break the bonds for the DNA of the cancer cells. Beta particles, that we mentioned many times in the industrial application, they have not as much energy, but they travel further and they can target as well. Also, there's something called Auger emitters. They too are a particle, similar to an electron, but not as much energy and therefore not going to travel as far. What makes it targeted is that the clinicians and the doctors and the scientists that are working on this attach this biological targeting material. So basically this targeting, and it says here on the slide, this vector, it will have an affinity to go to whatever the cancer cells are. So by attaching that targeting vector to the radioisotope, you are now delivering it directly to the tumor cells. And then based on whether it's a beta or an alpha, is going to give you that range of how far can it travel and what can it do, how much energy can it deliver directly to the tumor cells. Some examples of what is already out in the world right now. These are some of the beta emitters that have been out on the market. Iodine-131, again, has been around for decades. It is used in thyroid cancer. Your thyroid has a high affinity to want to absorb iodine. So by giving the iodine-131, it can go after the cancer in your thyroid. Yttrium-90 is used in a couple of different treatments. The same with the strontium-89, mainly for bone pelletation, because strontium is very similar in chemistry to calcium, so it will go to the bone. And the last one is the holmium-166 for liver cancer. Lutetium-177, you have probably heard a lot in the news, is in many trials. It's also one of the ones that has been approved by the Food and Drug Agency. And the final one that just also came out is the only alpha emitter that is approved by the FDA, and that is the Zyvago. That is actually delivering the radium-223. So again, switching gears, what else can we use radioisotopes for? Maybe not as direct applications as what we have just gone through, but they are exciting. Eric mentioned that was part of the discovery team for element 117 that was named tennessine because the University of Tennessee, Vanderbilt University, and Oak Ridge National Laboratory were all part of that discovery team. So this recognized the contributions of the state of Tennessee. Fun fact, this is the second element on your periodic table that is named after a state in the United States. The other one would be California. But we use an isotope called berkelium-249 that was generated in the high flux isotope reactor at Oak Ridge National Lab. It was isolated and purified and then sent over to Dmitriygrad and then eventually to Dubna, Russia, where it was bombarded with another isotope, calcium-48, and the reaction of the calcium-48 radioisotopes against the berkelium-249, you add the two together, you get 117. But it's not that simple. It took about 5 months of bombardment, and we only got 6 atoms of 117, but it was still exciting. Some of the other actinides, now to remember, if you look at your periodic table, the actinides are the very bottom row that you rarely get to talk about, but they are the ones that are doing some very exciting discoveries. So I've listed here the curium-248 is being used right now in Japan as they are looking for element 119. So they're doing a discovery experiment as we chat. Einsteinium-254, which we only make very small quantities at a time. It has some very unique nuclear physics properties. So those are being studied to look at what is actually going on in fission and how does that work. Plutonium-244 has an extremely long half-life so that we can use it to actually look at how plutonium behaves in the environment to understand its chemistry better. In archaeology, a lot of us always think of carbon dating, using carbon-14 as a way of dating items that we have found. Carbon-14 has I think it's a 5,700 plus year half-life. So as it decays, we look at the ratio between the carbon-12 and the carbon-14, and then we can ascertain what the date is. But if it's greater than that kind of time frame of that half-life, it's not going to help us. So carbon-14 is predominantly used for dating items that have been around more when we think about the human interaction with the world. They actually can use the uranium isotopes for dating older, the things that would be in the hundreds of millions of years. So we can use different isotopes for doing different archaeology uses. So if we can't find the isotopes in nature, then what do? Well, we make them. We have several pathways to make these, either through transmutation, which just means changing through by using accelerators or nuclear reactors. The radiochemistry, where we can actually do physical separation of different isotopes as long as they are different elemental elements. Or we can use the generators to melt off the decay daughter from a parent radioisotope. And then we also have something new, which we consider harvesting off of a beam. So yes, this is busy. It's got math on it, and my arrow's in the wrong place, so I apologize. But this just kind of gives you a sense of you can use different particles. You can accelerate different particles in these accelerators, and then you hit them with a target nucleus. And that target nucleus could be of a certain other material or isotope. And this block diagram on the left shows you that you have your original nucleus, but if you hit it with these different particles, whether it's a neutron, a proton, and you'll see things that sound strange, a deuteron. So a deuteron is a proton and a neutron, a triton, proton and two neutrons, a helium-3, which is basically two protons, one neutron. You can see where these numbers are coming up, or an alpha particle, which is the helium nucleus, two protons, two neutrons. But when you hit them with these different projectiles, a couple of things are going to happen. Either you're going to completely miss it, and that's the scattering. You're going to graze it, meaning you'll hit it, but it doesn't really react. Or you're going to hit it and you're going to get this formation of a new target nucleus. And that's the one we always want to shoot for, is that getting that formation, that compound nucleus. It's very similar when we talk about it in a reactor. Very, very similar. And so the idea is you start with a target nucleus, and in the reactor, it's typically we're going to be using neutrons. So the neutron will interact, and if it interacts and the nucleus doesn't get overly excited, it's going to move on to the next isotope. So in this example, if I start with curium-244 and I hit it with a neutron and it absorbs into it, I get curium-245. But curium-245 is a challenge. If you see in the parentheses at N, F, it likes to fission. So 90% of the time, a neutron will interact and that nucleus will fall apart. It will fission. But some of it will go on to the curium-246, which will then go on to curium-247, which it likes to fission, but not as much. 248. And then we get to curium-249. Curium-249 is fun. You'll see it's got the beta minus symbol. Beta decay actually creates a proton. So a neutron is actually converted to a proton, and that's why it goes up diagonally to the left. So the curium-249, when it decays, goes to berkelium-249. But then it neutron captures to berkelium-250, beta decays up to californium, we neutron capture, beta decay, and that's how we move up in our elements to go all the way up to fermium-257. That is as far as we can go in a reactor system. So due to physics, that is as far as we can go. If we want to go further, we have to use those particle accelerators. And that's where we got the remainder of the actinides through 103, and then the super heavy elements to go all the way up to element 118, which is oganesson. So in radiochemistry, I mentioned this idea of a generator. So a generator is if we could load the radioisotope of interest, and then it decays into a different isotope that's also a different element, then we can use chemistry, because we can separate elements, different elements, with chemistry. We cannot separate isotopes with chemistry. We need to use a physical means to separate isotopes based on their mass. So in the generator, we could say have a parent radioisotope that either decays by beta or decays by alpha into a different element. And then by using the chemistry, using a certain molarity of an acid, we can strip off the isotope of interest. That is how a lot of the medical isotopes, what they call medical generator, that is the mechanism for them. So there is that's one way of how this Zephago works. The radium-223 is a daughter of actinium-225. It's also for the tungsten rhenium applications. So this is a way that you can load the radioisotope and send it to the medical facility, and then based on the half-life of what's loaded, get the decayed product, and that is what is used for the labeling or the treatment. These separations, as I mentioned, mass separations for isotopes, those are things like gaseous diffusion, liquid diffusion, laser diffusion. We can use lasers to separate, and electromagnetic isotope separation. So there's multiple methods to do isotope separation. We can also take advantage of those chemical separations, those chemical differences, and we use things like ion exchange resins, both cation and anion, also solvent extractions using different organics, because certain elements have an affinity to be in the organic phase, while others would prefer to be in the aqueous or the water phase. So we take advantage of all those differences to do these chemical separations. Harvesting is fairly new. There's a brand new facility up at Michigan State University that's come online. It's called the, I always forget what the F is. Oh, Facility for Rare Isotope Beams. So using these rare isotope beams, you accelerate them, and that's your primary beam. But then by using magnets and bending it, you can strip off which ones you want to get that whatever beam is specific to that isotope. But then there's this unused portion of the beam, which has a lot of isotopes in it. And that's what can go into a beam blocker. And from there, you can harvest off of that really unique and exotic isotopes. So this is a fascinating facility where we're still just learning of what can we actually get from isotopes, and then how could we use those isotopes. So that is a lot of really cool research that is going on today. So what I've also provided in this presentation were some, what I think were cool links for you guys to use in your classrooms or in your outreach. If anybody is old enough to remember Tom Lear, he did the periodic song to one of the musicals, and if my link works, we're going to go ahead and watch the animated version, but I've also got the one with Daniel Radcliffe singing it, and his is even funnier.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, magnesium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, and radon, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
So I have no idea if you actually saw that or heard it or anything, but it will be in the presentation. You will have access to it, I promise. So Eric, I think you get to cover this slide.
I do. So we have navigating nuclear, where we work with discovery, education, and put these things together. So we have stuff for elementary school, middle school, and high school. But specific to what Julie shared tonight, we only have things that can be done for middle school and high school. So, and in those, if you look, we talk about measuring radiation, planting seeds for cancer patients. Those are those radioisotopes that Julie talked about. A thing on realities of radiation. Then we talk about decoding decay, how you can use different decay to be able to look at things. If we go down and look at that pesky mosquito from North Carolina, it looks like to me. Julie talked about how to do sterilization, so there's a work plan to do there. A little bit on exploring. We have kind of a detective one. If you look there on for artwork to see, you know, is it a forgery? Is it truly the right sort of thing? And then we also have, to back up what Julie talked about, was the radiopharmaceuticals that you could kind of figure out, you know, which one would work, why do they do that, and it kind of emphasizes more on what Julie was doing for the classroom. So those are what's available to all of you. There's no subscription charges or anything. We had ours. All the stuff that we did with Discovery Education is in the public domain. And this slide covers, it'll be in your packet, about the educator training that we have, and those help you, the high school, middle school, elementary school, with these webinars. We have ambassadors like myself and Julie that can go into the classroom or interact with you virtually to help you out if you have questions. And then we have these in-person events to inspire students. You know, I get probably an email every month or so to answer some sort of thing with the science. So we as a society are here to help provide that technical information that you need in your classroom.
And as I had mentioned, these are all links. Many of them are where I got the information for this presentation from. I hope they are helpful to you. And if you get and have any questions on this presentation, you may certainly reach out to me. I'm very easy to find, as Eric was kind enough to point out that I have a Wikipedia page.
Well, she didn't put it on her bio, and I just thought you gotta figure out how these Tennesseans, why they named the element there. So you got to see it. I haven't seen it yet, but I will.
So that is the end of my presentation.
So we have a question, and I'd like some review on this one too. On the isotopes, we have the M after an isotope. For example, tin 117M. Tell us about that metastable thing.
So you can have an isotope in different states, different excited states. And so the metastable that's what it means. It's just not quite stable. And so one isotope can actually branch and have two different half-lives and two different decay modes. And so that was just the letter they got, was metastable.
Okay, thank you. Let's see. So we have another person that gave us a different song. So we'll put that in the link for everybody to take a look at. We have a question on what kind of regulations and monitoring are there for these small radioactive sources out there in industrial devices?
Well, most of these are going to be regulated by the Nuclear Regulatory Commission. So the NRC is going to regulate these. The ones that are small are sealed sources, so they have to meet very stringent regulations. They're also very small quantities. And there's also, if you're small enough and you meet those regulations, you're considered non-exempt. Some of the sources that we use in the classrooms are encapsulated and they're considered accepted sources. If it's one that's going to be used in the field, that's a much greater concentration. Those industries have to be trained, have to be qualified, have to be registered with the NRC or with their state if they're an agreement state. So there's a lot more controls on those. So it really depends on the fabrication of the source, the activity or amount of the source, and how it's going to be used. But bottom line is it almost all comes down to the NRC.
Okay, let's do a different bottom line. One of the trivia facts is that technetium didn't exist and chemists predicted it. Nuclear power comes along, we have technetium. So one of our participants asked, why didn't you talk about technetium, the Moly-99 to technetium metastable? Can you give us a little bit more on that generator, please?
I'm so sorry. I'm just not as familiar with that one, to be perfectly
Okay.
honest. What that one is very specific, and it's in a different part. It's just not in my world, so I apologize. But it's definitely one you can certainly find a lot of information out there, since it has been around, oh gosh, probably since the 70s as far as a medical application for it. And it also is the workhorse in today's world. So it is the most prominent. And so I am remiss that I did not put it on, but it was purely due to my ignorance.
Okay. And I'm not too sharp on technetium myself, so good question. All right, we had a question on, are there certain types of cyclotrons or accelerators that are used to make radioisotopes for pharma?
Yes, I don't have the details onto what those are, but yes, you only want certain energy levels, and there's energy levels, there's microamps. So yes, you want them tuned to what isotope you are going to make. Very much like a research reactor can make different isotopes than what a commercial nuclear reactor would be able to make. And it comes down to the number and energy of the particles. So yes, there is, and again, I'm a reactor person, not as much of an accelerator person.
Okay, and one company, their ANS members is called Shine. They're up in Wisconsin. That might be a good resource for the teachers also. What they're doing. I've lost track. They were colleagues at school, and they.
I don't think they're using an accelerator though.
Oh, okay.
But universities like Texas A&M, University of Alabama, University of Wisconsin all have accelerators and cyclotrons in their programs, and they are making small quantities of radioisotopes for medical applications. You could go to their websites and get a lot of information.
So there's a question about one particular teacher the students have interest in, and the question is, can you talk about how stored radioactive waste is repurposed? Is there anything?
So if we could recycle radioactive waste?
Well, it says that, and then the comment goes on. I remember watching a video that talked about creating element 117 and 118. Students are always interested in why so much effort goes into producing a few atoms of synthetic elements. Is it really possible to do something useful with so few atoms, especially if they're likely to decay quickly? When you talk about one more paragraph, when you talk about harvesting isotopes, is this different from using something like a mass spectrometer? Is a mass spectrometer only for stable isotopes? How do you isolate isotopes? So a lot's packed in there.
Sure. So going back to the super heavy element, why do we only make 6 atoms of something, right? That's a fair question. It's because physicists and chemists want to keep pushing the boundaries of science. So that's one reason, and to understand how our universe was formed, right? Also, Glenn Seaborg had a theory that there is this island of stability somewhere out there on the periodic table, that if you get the right number of neutrons and the right number of protons, these will last more than microseconds, that we will have stable radioisotopes somewhere out there. And the question is, what would their chemistry be? Could we use them for something exciting and new? And the example I will use is the americium-241. When americium was first discovered as an element, its isotope was incredibly short. It wasn't the 241. It was a different isotope. And so who would have known that eventually we could make a different isotope of americium, and it would be able to be used for this application of smoke detectors. So we don't know what these new elements and what their isotopes could make someday. So it's the understanding the nuclear physics, but it's pushing it to understand what the chemistry might be. Going to the harvesting, there are multiple ways to harvest. I gave the example for the big facility up at Michigan State, but you could harvest and from other processes, right? If there was a way to chemically separate an isotope of interest, but there's got to be enough of it to be able to do it. And one example that the Department of Energy is working on is harvesting promethium-147, which is a beta emitter. And it's actually coming from the making of plutonium-238. In the process of isolating plutonium-238, you have a lot of fission products. You have a lot of promethium was made in that process. So you can recover the promethium from the processing of the plutonium through a lot of radiochemistry. It is a lot of purification. So there are ways to harvest isotopes from other processes. So those are things that are being evaluated. I can guarantee you they're being evaluated on many levels. Did I capture all of them?
Yeah, I think he caught that one well. And then just to stir things up, you know, it's more than 5 atoms that they made. But so they made more than the points that the Vols will score against Alabama. Just to stir.
Cool.
Oh, okay. That's mean. I didn't go there. Okay, so here we go, Julie. Are there DOE's facilities the only source of making radioisotopes? Or are there other sources, say, for americium-241? Are there any commercial entities?
It depends on the isotope, right? So for americium-241, right now, I believe the only place you're going to get it from is through the Department of Energy. But there are other isotopes that are made commercially all the time, right? When I mentioned about the positron emission tomographies, the PET scans, those are made, the fluorine-18 is made on site with PET scans because the half-life is so short. They have a small cyclotron and they can make the injection right there. So, and also we know, like we mentioned, Shine is making, I believe, lutetium-177. And then you have the Europeans in their market. So there are commercially available radioisotopes that can be made. If it cannot be commercially made, and there is a significant need for that, and it's a critical, then it's going to fall on the Department of Energy, because that means it needed resources that industries does not have, such as a high flux isotope reactor or a certain type of accelerator, or doesn't have the hot cell facilities to safely process the material to get the purified product out. But if it can be made commercially, it will be made commercially.
Okay, picking on your element again, sorry, and I don't pronounce it right, so I'm not going to say it. So the Tennessee element. So the question is, was the isotope produced and which led to its discovery in nature? So I don't.
So tennessine is completely artificial, completely man-made. There were 2 isotopes that were isolated in it. They differed by 1 neutron. And the way that you actually in super heavy element discover is that it decays into something that's already known. And most of these super heavy elements are decaying by alphas. So again, that helium nucleus, 2 protons, 2 neutrons, a lot of energy. You know, we're talking 7 million electron volts. Remember, we talked about strontium only decays giving off 1.09 EV per decay. These alphas are giving off millions. So they can be detected. So the way when you're making these new atoms is you're looking when that stream goes through these very elaborate detector systems, you're looking for the detector seeing that same event in multiple detectors. And it sees that event, it sees how much energy was given off. And then that decays into something else. And then you see that energy. And so you're looking for that chain of energies, those alpha decays, saying, okay, we know 117 goes to 115. Well, 115 had already been discovered. So when they started seeing those decay energies of 115, they could back calculate and say, okay, that is a new element. That is element 117. So it's very fascinating that that's how you do a discovery, is through its demise, is through its decay, and looking for those energy signatures. In fact, when they did the confirmatory measurements on 117, and it's just tennessine, I-N-E, just like fluorine, tennessine.
Tennessine. Okay, sorry.
That's all it is. When they were doing the confirmatory, the decay into element 115 was so solid and so strong that Oak Ridge National Lab, that team, we also got credited for the discovery of 115. So it's just interesting how nuclear physics works.
Thanks. There's a question on, and this, are there applications for radioisotopes in mass spectrometry?
Well, I know mass spectrometry is used to detect, well, that's how we use it to detect or actually quantify our isotopes. But I believe the answer is yes, but again, I'm getting out of my knowledge zone because when I talked about the airport detector system, that is an IMS. I can't always forget what it's ion mass spectrometry, but it is, that's the technique that's used using the nickel 63 to look for the organics. So I think the answer is yes, but that's a good one for me to follow up on.
Okay, so I'm going to ask you this question, and then I have an answer too, because I dabbled in this just a little bit, but I'll let you go first. Are there applications for radioisotopes in fighting climate change?
In defining climate change?
No, in fighting. Sorry, I didn't. Fighting.
Well, of course, you and I would both argue that if we had more nuclear power, whether it be fission or fusion, that we would reduce the carbon levels in our atmospheres. I mean, that's our answer.
So how about, let me answer for you then. So there's this other national laboratory called Los Alamos National Laboratory, and I forget the individual's name. It was when I was working at Idaho National Laboratory, was doing research on alpha particles in breaking down carbon dioxide. So he was injecting or launching alpha particles. So one alpha particle can break the bonds of 1 million carbon dioxide molecules. So you end up with CO and oxygen. And then that CO is a little bit more reactive, and you can do things with it to sequester it or make other products. And that particular person did a whole bunch of work. I put in a proposal within the lab and never got it funded. So that's the only thing that I've seen, because realize the carbon bonds for carbon dioxide, measure in electron volts. And here you have this, you pick your alpha particle at 5 million electron volts, it just rips them apart, causes ionization, and then he had a way to separate it. So that's what I've heard about. I don't know if you see that anymore, Julie.
I have not heard about that. So again, another one I need to go take a look at.
Yeah, and I forget the individual's name. He did the work. I don't have access to that anymore, but it was out of Los Alamos, and he had a chamber, and he had CO2, and he had alpha emitters, and he was doing that sort of calculations. What if I got all the alpha emitters from used fuel and did the math and made plates and stuff? So there's a possibility for your next PhD, or not PhD, Nobel Prize.
No.
You got a Wikipedia page. You need to have a Nobel Prize. All right. So next question is, are there teams looking to produce alkali metals or precious metals like the materials needed for batteries using nuclear transmutation?
Not that I'm aware of, because I don't think you'd want radioisotopes in those products.
Okay. Is the plutonium radionuclide used for RTGs? Did it come from fission fuel of nuclear reactors?
Plutonium-238, there's a little bit that would be made from the uranium fuel in reactors, but to efficiently make uranium-238, you transmutate neptunium-237. That is to make the quantities that NASA needs for their applications. That is the effective way. So what small amounts are made during a reactor operation are not going to be sufficient to harvest.
Okay, this one, I'll read it verbatim. NRCs allowing state level agencies to regulate transport, storage, etc. of radiopharmaceuticals within their state, ?
Well, yeah, the NRC, through the NRC and the Department of Transportation, DOT is what will regulate radioactive materials. They're labeled under hazardous, but it's hazardous radioactive materials. You have to follow the DOT regulations. So the fabrication, the packaging, the fabrication could be done through NRC regulations or DOE, depending on where it's done. But once it's transported, you're going to fall under the Department of Transportation regulations. So packaging, labeling, marking, shipping, handling, that documentation, that will all be under the Department of Transportation. I believe it's 49 CFR, like 172 to 174. Yeah, the only reason because I've done some of this. So it's very regulated from the Department of Transportation.
Sure. All right, back to plutonium. Also, what are the potential of utilizing plutonium as a fuel for deep space exploration?
My understanding, it's the same application that you would have for deep space. Deep sea would be a similar environment to deep space. And you're still using that concept of a radiothermal electric generator, the RTGs. Now, I'm not aware of where the applications are as far as maturity of that technology, but my understanding is it can be used in that same application.
Okay. Well, you have worn them out because there's no more questions. And we got 4 minutes left. So, on behalf of the American Nuclear Society, I really appreciate all of those that showed up to the webinar. Julie, I appreciate you spending some time with us and sharing your wisdom with isotopes. It's, had a long career, and we look forward to your Nobel Prize in CO2 destruction. And somebody put a link of, there is work there. So we just need you all to take it over the edge to make it practical.
Wonderful. Well, thank you again. I love the opportunity. And again, anybody can send questions my way and I will do my best.
All right. Thank you so much.
Thank you.
Good night.
Night.